All right. So we're going to keep looking at those sequences that we've been practicing with. So we get to bump up. We're still in that section 2 of our appendix, but we get to talk about topic 2, which is we're going to look at arithmetic sequences. We've already started to look at these. So when we were just starting talking about sequences, we sat there and knew that there were 2 types of sequences. Anybody remember what they were?
Geometric.
Yep. Geometric and arithmetic. I know. Most people always pronounce it wrong, and that's fine, right? And arithmetic sequences. So, and then we kind of briefly talked about the difference between a sequence and a function. So when we talk about functions, like generically, a lot of times we write like that f of x, right? But when it comes to a function, we know that when we graph these are going to be continuous. So if I made like a cheesy little like x, y, and then I went to graph it like that, would be an example of a function, right? It's continuous. You connected all of the dots in that nice little swooshy like motion, right? But we want to talk about sequences. Anybody know if it's not continuous what it's called? Started with the D. I-S. Discrete. Yep. No, you're good. Good job. Yep. Yeah. So, like an example of like a sequence, like we always go back to like the number of buses. We can't connect all of the dots because we can't have 1 1/4 buses or 1 1/2 buses. You either have 1 bus, 2 bus, 3 buses. So when we graph sequences, it's discrete. So we're still going to have points like somewhere on the graph, but we're just not going to connect them. And when it comes to function, a lot of time we write f of x. So in this section, just to know the difference if you're looking at a sequence or if you're looking at a function, for sequences, we're going to write it as, that's really bad. I've been like wearing my contacts again, and I'm not used to them, and I'm getting old. We use the notation like n of t. Instead of that f out front, we put the little n out front, and that's just to help us know that we're talking about sequences. Well, we kind of go through these good little guys. So no different than a function. On a function, we can figure out what the equation is, right? We can do the same thing when it comes to our sequences. We can figure out a function. If I were to actually go through and graph these lines, oh, I guess I have a little pointer. I should use my little... If I were actually to graph these and connect these points, what would I make? I'd make a line, right? So when it comes to us coming up with our equation, we're really coming up with an equation for a line, except the only difference is we're not connecting all of our dots because we can't. So, all right. Do you know some equations for a line? See if we can. Anybody remember any of them? Y equals, yeah, mx plus b, right? What's this m stand for? The slope, yeah. What's our b stand for? the y-intercept. And the x and y are all of our points that are on a graph, right? Coordinates are x, y's. So those are all of your coordinates. So when it comes to a sequence, it's really going to be the exact same thing. B is going to be your y-intercept. The only difference is m instead of the slope. Remember when we found those common differences? How did we get from one number to the next? Well, same thing happens when it comes to a line, right? You're figuring out that slope. You're trying to figure out how do you get from this point to this point. So the same thing happens in a sequence. So that common difference that we find, that's going to be the m. Anybody know another equation? Yeah. Y minus y1 excuse me, equals m x minus x1. M stands for the slope. Excuse me. And then this x1, y1, that's just like a very particular point, right? One of the points that's on the line. All right. Ready to look at a fancy sequence? Maybe. You have to tell me if it's a sequence. What if we had, if I gave you -9, whoops, -9, -5, -1, 3, 7. Do we think that that's a sequence? Yeah, sequences is just a set of numbers, right? My ... is telling us it's going to continue. It's going to go on forever, right? So now we need to figure out, do we think this one is arithmetic, geometric, or neither? We could have a neither in there. Arithmetic, right? So we're going to sit there. How can I go from -9 to -5? What could I do? I could add 4. And then it's just got to work for all of them. If I add 4, does this work for all of them? Yep. So since I know that I'm adding 4 onto all of those, then we know that it is arithmetic. Right? And then we'll say that whoops, that's a C. Our common difference is 4. Right? And then sometimes they'll call those like a sequence generator. Like how do you generate from one number to the next? You add 4 onto it. All right. And then I know we talked about each one of these numbers, and we refer to each one of these numbers as starts with a T, a term, right? So what's our first term in our sequence? -9. What's the fourth term in the sequence? 3, yep. And we'll get into this a little bit more. So a lot of times when we want to find our terms, we use the letter A. So instead of always writing out first term is -9, A is the term that you're looking for, and then a little subscript, like a little tiny one. If we want to know A1, that's going to equal -9. So this would be A sub 4 equals 3. And then you don't have to write fourth term out every time. What would, I don't know, what do you guys want? A to the, what term? 7th term? Let's try 7th. We won't go too far. So if I wanted to figure out A sub 7, I'm saying what's the 7th term? What's the 7th term going to be in our sequence? Which one is it? 15? So what do we have? 1, 2, 3, 4, 5, right? So what's our sixth term going to be? 11, yep. So then our seventh term is going to be 15. Could we figure out our A0 term? How would we figure out A sub 0, or the 0 term? What number is this guy? He's our... I didn't hear him. Negative 13? How'd you get negative 13? Yeah, you got to go back, right? So if we're adding to go forward, we're going to subtract to go back. Whoop. Okay. And we're going to get negative 13. Yep. Sweet. Look at you guys cranking through these little sequences. Mm-hmm.
3 points, I need it.
Absolutely. Absolutely not. All right. So you can also take your sequences and our terms, and we can actually turn them into a table. I'm going to squeeze it down here. Just to try and keep it all on the same page. Right? So we're going to say that our first little spot is n, and then this would be our n of t. So no different than input and output. Okay? So our input is what term we're looking at. So n is always the term number. And then your n of t, that's like your output, or what you get. So we kind of say it's like the term in the sequence, I guess. So if we want to, what did we get for our 0 term? Negative 13. Yeah. What's our first term? What's our second term? Third term? Fourth term? Fifth term? Right. And you can keep going if you wanted to. I ran out of room. So our whole goal, a lot of times in Algebra 2, is to have 3 types of representations, right? We want to be able to represent it as a table. Can we do that? Could we represent this as a graph? How would we represent it as a graph? Yeah. Make our little table, or our little graph. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm running out of room. So let's see what happens if we plot these points. Oh, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Looks like a little skeleton up there. Halloween. So where do we want to put one of our points? Could we go 0, negative 13? We put one there. This is telling us the point 1, negative 9. So over 1, down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we got the point 2, negative 5. Three, negative 1. 4, 3. 5, 7. Should we connect the dots? Yes or no? No, right? Because we have a sequence, not a function, right? But if we were to connect the dots, what would we get? Well, perfectly drawn world, it would be a straight line, right? So if we have a table and we have a graph, I bet you we could come up with an equation because we know it's going to make a line, so we just have to figure out that equation for the line. Yep. Yep, absolutely. Yep. So y equals mx plus b, right? Which one of these do we know right now? Yeah, we know the y-intercept, right? So y equals mx minus 13. We can go there. So now you have a couple different ways where you can find m. Finding slope is the change in y over the change in x. So you can sit there and plug in, figure out the m that way. Another thing you can always do on these, because this x and y is a point that's on the graph. It actually represents like all of the points. So you can pick any point that's on the graph and you can plug it into the equation and solve it for m. So if we go back up to our table, what's a nice little pretty point you want to try? Any of them being like, ooh, I like that one. You guys like positive numbers? Pick positives. Mm-hmm. Which one? 4 and 3. That'll work. So let's try it with this guy, right? So what am I going to put in for y? 4 or 3? 3. Yep. Equals m. We don't know what m is. What are we going to put in for x? 4 minus 13. So now we just have an equation we got to solve. Add 13 to both sides. So we're going to get 16 equals, and I'm just going to write it as 4m, just because I think we were used to seeing it that way a little better. What are we going to do? Divide by 4 to both sides. What's my m going to equal? 4. So now when I go back up to my equation, now I know my m. So what do I get? Y equals minus, bam. So were you able to represent a sequence by a table? Were you able to graph it? And were you able to come up with an equation? Look at that. You guys are golden then. Oh, domains and ranges. Do we have domain? What's our domain? Domain are always your inputs, right? So those are all of your domains. Range is your outputs. Yep. And what did we get out? All of these guys. Okay. You guys remember which one's independent and which one's dependent? Yep. All right. And then now that you have this nice little fancy equation over here, think of a crazy number. What number? Give me a number. Well, we got to go higher than 7 because we kind of figured out the first 7 terms. Figure out a number bigger than 7. 10. I like 10. So if we want to figure out our 10th term, you know how we have y equals 4x minus 13? Where do you think the 10 is going to go in? It's going to go in for our x, right? Because that's our input. So y equals 4 times 10 minus 13. What are we going to get for y? 40 minus 13, yep, which is going to give us 27. Good job. So we didn't go too far out in the sequence, but instead of going through like we did up here, where we just kept adding 4 and adding 4 and adding 4, granted you could have done that to get to the 10th, right? That would just be adding it, you know, a couple more times. But we sat there and used, if we were to figure out the 120th sequence, I don't think you want to sit on your paper and keep adding 4 until you get up to 120, see the 120th term. So that's when the equation comes in nice and handy to figure out the value at that term.